Hi everyone, my name is Sans. I'm from the Cidp team and I'm going to explain what we did in this project. So basically
what we did was merging Smode algorithm, which is the synthetic minority oversampling. Synthetic minority class oversampling technique algorithm with the deep learning, which was inspired by this paper called Deep Smode. And we changed the architecture in such a way that the oversampled data, the output that we received, is much more accurate than the original Deep Smode.
The important thing that you need to know about the Smode algorithm is that it's a linear interpolation technique. That means it works best with low-dimensional data, and when handling high-dimensional data such as image data should be dealt with really carefully so that Smode can be applied directly to it. And that's where the autoencoder comes into place.
I'm going to start by showing you the final result of our research and then explain how we got the better result as compared to Deep Smode because of the improvements that we made in the architecture. As you can see, the ACSA, GM, and F1 score, except the GM score, we have received a better ACSA score and F1 score with our HD Smode model for both MNIST and FMNIST dataset. Now I'm going to explain the architecture of the HD Smode model. It consists of the structuring autoencoder, the Smode algorithm, and the loss function. The structuring autoencoder is used to reduce the cluster overlapping between different classes when the autoencoder embeds data into the latent vector space.
Now, if that didn't make much sense, here is Jihyun explaining through a Zoom call about how the structuring autoencoder actually works in practice and in code.
9 cluster over here, right? A 0 cluster over here should be distanced, right? Should have a certain distance to be clearly separated, right? So this is the point of the structuring autoencoder. When we just use an autoencoder, it is not easy to get a clear cluster division like this.
Next, we have an enhanced Smode algorithm for multi-class data. We can see that a simple Smode gives a result in such a manner, whereas borderline Smode is more clustered within its own class. We can see a similar pattern for LN Smode.
And what we are trying to do is basically train the structuring autoencoder with this as the loss function. And this loss function has 3 terms. It includes the MSE, the mean squared error of the autoencoder itself. It also includes the structural loss and the permutation loss that is obtained in the difference between the structure of the latent vector space. And this is how the loss term is formed. Gamma, delta, and epsilon are the hyperparameters that add up to 1. Now that I've explained individual parts of the architecture to you, I'm gonna explain how it all comes together. We have the imbalanced data set. Using the encoder, it is made into a low dimensional data from the high dimensional data because it's an image. Then it is structured in the latent space and then decoded. That loss is happened many times, and then it gets trained. So this model is becoming trained. Then what happens is we use the trained model to input images of the unbalanced data set, and on the trained encoder we run the Smode algorithm, which is the enhanced Smode. Then the enhanced Smode gives us oversampled output decoded by the decoder, which is pretty accurate. Here are what the results from the autoencoder training phase look like. Thank you for watching, and please make sure to like, comment, and subscribe.